x approaches infinity of 3x cubed minus 4x squared plus 6x plus 15 over 4x cubed plus 12x squared minus 30. Okay? Now, in order to use our limit laws, or in order to use those theorems, we have to have reciprocals of x, right? Okay. And like before, I'm going to do some calculations and show why each step makes sense, but in practice you don't have to do that. Okay? Well, I'm going to multiply by 1, and that doesn't change the value. But I want to multiply by an expression so that I get reciprocals of x. And I want to multiply by 1 over x cubed. Okay? And I'll write down why I'm dividing by that, or multiplying by that. X cubed is the leading term of the denominator. That's almost true, right? Leading term without the coefficient. Okay, x cubed is the leading term of the denominator. And you'll see how this generates the appropriate expressions whose limits I already know. So 3x cubed times the reciprocal of x cubed is just 3. And that's good, because that's a constant, and I know the limit of a constant. Right? Over here we have minus 4 over x. That's good because that's just 4 times 1 over x, and I know the limit of 1 over x. Plus 6 over x squared. Well, we'll talk about that in a second. 15 over x cubed, etc. Okay. Now, we're going to do a couple of steps in one. First, this is a quotient, so we're going to say the limit of a quotient is the quotient of the limit. So I can take the limit of the numerator and denominator separately, provided each exists. But now, once I'm at the numerator, I have several terms that are added and subtracted, so I could use the limit law for sum. So the limit of the numerator is the limit 3 minus, this is 4 times 1 over x, so we can use the constant multiple rule and say this is the limit, 4 times limit of 1 over x. This is 6 times 1 over x squared, but we had the limit of a power is the power of the limits, right? The limit of 1 over x squared is the same as saying limit of 1 over x squared. Right? And similarly here, we're going to do something similar for the denominator. Okay. So what we've used here so far is just the limit laws, right? All those 6, 7 laws that we had a few sessions ago. But now at this point, all I need to do to actually compute the limits are those 2 theorems. Limit of 1 over x and limit of a constant. Limit of 3 is 3. Okay, minus 4 times limit of 1 over x, 4 times 0, plus 6 times 0 squared, plus 15 times 0 cubed, over 4 plus 12 times 0, minus 30 times 0 cubed. Okay, that's 3/4. Right? I've stretched this long enough, but again, like I said, we're just going to do this one time. So you actually see that it makes sense. Okay? In practice, what I would like to see you do is this this, and then the answer. Because from here already you can see that the limit of the top is 3, and these are zeros. The limit of the denominator is 4, and these are zeros, so 3, 4. Okay? But it's important to convince yourself that what you're doing makes sense. And in order to do that, that relies on previous theorems. All right? So just try to go through this once in detail and make sure you understand every step. Yes? Why can't we, okay, so this is what we have, right?
Yes.
Right? Well, limit of a constant times a function equal, we can take the constant out. Right? So we have 4 limit 1 over x.
But we can't do it for limit 3.
For limit 3?
For count.
That's a constant. It's a constant function. Okay? So the reason we're doing it here is because I know the limit of 1 over x. Only. Right? I don't know the limit of 4 over x. Technically, I don't. I just know the limit of 1 over x according to the theorem. But according to the theorem, I know the limit of 3 by itself. So I can keep it as is. Right? It's how your computations are justified based on the theorems that you have before. Three limit of what?
Okay.
Of 1? Limit of 1 is 1 times 3 is 3. That's the same thing. It's limit of a constant. Right? Okay, good. To figure out whether or not this line holds as an asymptote for the left side, I have to calculate limit as x goes to minus infinity. Okay? And things may or may not change. So let's see. Now if I remove the absolute value here, I have to put negative x cubed because x is negative. Right? And again, if you perform the algebra we did earlier, you see that the limit is negative. Okay? And since this limit is a number, y equals negative 1 is a horizontal asymptote. Okay? And again, by itself, not much, but with this limit tells me that that asymptote kicks in on the far left, okay? And has nothing to do with the graph on the far right. All right? Only kicks in on the far left. All right? So from now on, it's not enough to say whether or not you have an asymptote. You have to say where the function behaves like the asymptote. Okay? So the graph of that, by the way, looks like this. So here's 1. Here's 1. Okay. Here's negative 1. And the graph, if you graph this, looks like this. Okay? That's the graph of y equals x cubed minus absolute x cubed plus 1. All right? In previous classes, there's a misconception that your graph can't cross an asymptote. That's false. Okay? It can cross horizontal asymptotes. Okay. Limit as x goes to infinity of sine of 1 over x. sometimes we find it easier to do computations by making a simple substitution. Okay? If you consider t to be 1 over x, alright, then what do you notice? As x goes to infinity, t goes to what? 0. 0 positive or 0 negative? Positive. So, if you make that substitution here, you can say sine of 1 over x is the same as sine t as t goes to 0 from the right. Right? And that's, of course, sine of 0 is 0, so that gets close to 0. Right? Maybe not very instructive there, but definitely for this next example, x sine of 1 over x. Okay. Before we do any calculations, let's just think about this. When x gets really large, we have a product here. This number gets really large, but just as we saw, this number gets really small. Right? So this gets really large and this gets really small. So what happens to the product? So we can't really tell. Okay? But there's a clever way to write this. X can be written as the reciprocal of the reciprocal of x. In other words, the reciprocal of the reciprocal. Right? If you calculate this, then you'll see that it's the same as this quantity. Now, if you make that t substitution, then you notice that t goes to 0 from the right, and the expression becomes sine t over t. Right? And that's a limit we know. What is that limit? 1. Very good. Right? As a matter of fact, we can do something similar for x going to negative infinity of x sine 1 over x. And similar calculations give us limit as t goes to 0 from the left of sine t over t, which is still 1. Right? Let me remind you of the theorem. The theorem said limit as theta goes to 0 without any direction. So from both directions equals 1. So from the right or from the left, this limit will be 1. Right? Okay. To summarize these two statements, let's write it down here. We can just say that the limit as x goes to plus or minus infinity of x sine 1 over x is 1. Let's do another one. Limit as x goes to infinity of sine x over x. Okay, the point of all these examples is to show you that we've done a lot of theorems and a lot of laws of limits when x approaches a number. And a lot of those same theorems still work if x goes to infinity. Okay? So here's a really cool example of how that plays out. Note that we can't do the quotient rule. We can't do this. And you should think about why. Why can't we do that? Okay? Because what happens when x is large? What happens to sine x? Well, sine x is between negative 1 and 1. Okay, it doesn't approach any fixed value. So, in order to do the quotient rule, the individual limits need to exist, right? And since that's not true, we can't do that. Okay, but there's something else we can do. Sin x is always between two values. I just said, what were they?
Negative 1 and 1.
Negative 1 and 1. Okay. So if I take the absolute value of sin x, it's between what two values? Between 1 and 1?
Negative 1 and 1.
The sin, absolute sin x. 0 to 1, right? Absolute value of something is always 0 or more. And the largest value it can be is 1. Right? Okay. And let's go to this expression so we can divide by absolute value of x. Is that clear? We're just dividing throughout by x. 0 over x is 0, sin x over x, and 1 over absolute value of x. Okay. Now, this inequality is true for any value of x, right? Because where did that come from? That came from here, which is true for any value of x. Okay. What's the limit of, as x goes to infinity, of 0? 0. What's the limit as x goes to infinity of 1 over absolute x? 0. We might as well not write absolute x. X is positive. These two are the same. By what theorem? By Sandwich theorem. By Sandwich theorem, the limit of sin x over x equals 0. Okay? Okay. Let's take this example here. Limit as x goes to infinity of x minus square root of that thing. When x is large, this is really large, right? And this square root of a large number is large, right? So a large number minus another large number. I mean, we can't think of what does that click close to. It's kind of... It's infinity minus infinity. Which infinity is bigger? You know, that's the problem. And the limit theorem we have for this is 1 over x. I have to have a denominator. I have to have some reciprocal of x. And so we have to create it before we can do any computations. And we've worked with radicals before. What's the standard thing we do? X plus square root of x squared plus 16x. I mean, this looks nasty, but hopefully it'll actually lead to something we can work with, right? At least we have a fraction. So that's good. Okay, let's simplify this. So after simplifying, you get x squared minus this over this term. You agree? All right, so one more simplifying step. Negative 16x over x plus square root x squared plus 16x. Okay. Now that I have a fraction, I plug in infinity, I get negative infinity over infinity plus infinity. And so we can try to get some reciprocals here. What is the largest degree in the denominator? Is it x or x squared? X. So that is how we figure it out. The leading term here is x. the leading term in here between x squared and 16x is x squared. And the square root of that is x. So the leading term is x. So divide by 1 over x, or multiply by 1 over x, and let's see what we get. So negative 16 over 1 plus. Now, let me make a note here. 1 over x is the square root of 1 over x squared. And x is positive. Right? 1 over x and square root of 1 over x squared is the same thing if x is positive. And it certainly is when x is going to infinity. So when I want to multiply by 1 over x inside the radical, I can multiply by 1 over x squared. Okay, that's the equivalence. It's 1 plus 16 over x. Is that clear? Okay. Well, actually, at this point, I think we're good. What's the limit of the numerator? Okay. Limit of 1 is 1. Limit in here, that's a 0. Square root of 1 is 1. So 16 over 1 plus 1, negative 8. Okay. A line y equals b is a horizontal asymptote of the graph of y equals f if one of two things happen, or both. If the limit at positive infinity is L, or the limit at negative infinity is L. Of course, nothing sacred about L. It's just saying that if the limit as x goes to infinity of the function is a number, then I should say L here, y equals L. Then y equals to that number is an asymptote, is a horizontal asymptote. A horizontal asymptote, what does it look like? Well, here's the picture. What does y equal L look like? That's a horizontal line, right? So, in this graph, we have two horizontal asymptotes, y equals to negative 1 and y equals to 2. Okay? And the relationship between these green lines, the horizontal asymptote, and limits is a very close one. Okay? This behavior that when the function is getting really large, the graph of the function turns and looks more and more like the horizontal line y equals to 2. That part is telling us the limit as x approaches infinity of the function equals to 2. Okay? The larger x gets, the closer the function values get to 2. Okay, and eventually it looks more and more like that line. And this part tells us that the closer x gets to negative infinity, in other words, the further left that it goes, the function values get close to minus 1. So limits at infinity give us some good idea about how the function behaves on the far left or on the far right side of the graph. Okay? And to find those horizontal asymptotes, we actually employ these limits at infinity. example here. So find the horizontal asymptotes of y equals x cubed minus 2 over absolute x cubed plus 1. Okay? Well, like that definition says, to look for asymptotes, I have to study the limit as x goes to infinity. Now, if that equals a number, then we have an asymptote. If that limit does not equal to a number, then we don't have a horizontal asymptote. Okay? So, here's my function. Okay? Let's see, before I can do that stuff I did, dividing by the leading term, I have to get rid of this absolute value. So, an absolute value, in order to remove it, I need to decide whether x is positive or negative, right? Here, x is positive. Why? Because x is approaching positive infinity, so it's a positive number. So we can just remove the absolute value without any change. And this is going to equal 1. Okay? You can do calculations similar to the one I did earlier. So what does that mean, though? That the limit as x goes to infinity of this function equals 1. Well, it means that y equals 1 is a horizontal asymptote. Okay, but that's a little misleading. If I just say y equals 1 is a horizontal asymptote without showing this, right, then it's kind of misleading. Because, for example, y equals negative 1 is a horizontal asymptote here, but it tells us nothing about what happens on the right side. It only tells us something about the left side. So this sentence by itself tells us that either on the right side or on the left side, the function behaves like this line. Okay? But if you match this up with your limit calculations, then it's telling us that this line kicks in when you get far right. Okay? That's all we know. To figure out whether or not this line holds as an asymptote for the left side, I have to calculate limit as x goes to minus infinity. Okay? And things may or may not change. So let's see. Now if I remove the absolute value here, I have to put negative x cubed because x is negative, right? And again, if you perform the algebra we did earlier, you see that the limit is negative. Okay? And since this limit is a number, y equals negative 1 is a horizontal asymptote. Okay? And again, by itself, not much, but with this limit tells me that that asymptote kicks in on the far left, okay? And has nothing to do with the graph on the far right. All right? Only kicks in on the far left. All right? So from now on, it's not enough to say whether or not you have an asymptote. You have to say where the function behaves like the asymptote. Okay? So the graph of that, by the way, looks like this. So here's 1. Okay. Here's 1. Okay. Here's negative 1. And the graph, if you graph this, looks like this. Okay? That's the graph of y equals x cubed minus Okay. We've made the relationship between limits at infinity and horizontal asymptotes. And we said that we have a horizontal asymptote if the limit at infinity equals a number. What if it doesn't? For instance, let's take this function. Let's take this function. F of x equals x squared minus 3 over 2x minus 4. Okay? And let's study the limit as x gets large. Okay? With a similar computation, if we say multiply by the reciprocal of the leading term of the denominator, then we get an expression like this. Okay, so we hold off this term for a second. 3 over x goes to 0. 4 over x goes to 0. The limit of 2 is 2. But x goes to infinity. X gets really large. So this limit is infinite. Okay? In other words, the limit does not approach a number. So there's no horizontal asymptote here. But what this is telling us is that as x gets large, y gets large. Okay? That means the graph lives on the upper right corner of the xy axis. When x gets large, y gets large. So as x gets large, we're on the top right corner of the first quadrant, right? Okay. But when y is going to infinity, there are many functions that go to infinity. For example, y equals x squared. The graph of that is a parabola, and as x gets large, y gets large. Okay? Y equals x. Same thing, as x gets large, y gets large. So these are simple functions that the limit as x goes to infinity is infinite. Right? Y equals square root of x. Same thing, as x gets large, y gets large. But as you notice in all of these cases, y is going to infinity at a different rate. Okay, this is going to infinity like a parabola, this is going to infinity like a linear function, this is going to infinity much slower. Right? And I just said something about different types of infinities and how fast you go to infinity and so forth. Now this function is a little more complicated, so I'd like to know how this goes to infinity. Does this go to infinity like a parabola or like a line or like a square root function or what? And in order to study that, we typically would break up this into terms that are dominant and not dominant. With rational functions, there's a very standard way of doing that. Okay? And the standard way of doing that is to do long division. See? We're going to get this same result when the numerator degree is larger than the denominator. Okay, that's when we're going to have an infinite limit. So if I do some division here, okay, so just long division with polynomials, pretty standard. X squared over 2x is that's too far off. Let's bring it down here. X squared over 2x is x over 2, and then multiply. change the signs and add 2x over 2x is 1, multiply, change the signs and add. So we have a remainder. Okay, but more importantly, what this is telling us is that I can write that function quotient plus remainder over divisor. Okay? That's the same function, just written differently. Now, as x gets large, this quantity gets really small. Does that make sense? Okay. But this quantity is large. So here's what we're going to say. As x gets large, f of x is approximately x over 2 plus 1. Because this part is negligible. So it's like saying, if x is like a billion, this is like half a billion plus 0.00001, for example, right? So f of x is approximately this value when x is really large. So in that case, when x is large, the function graph would look like x over 2 plus 1. Okay? Let's draw that. Let's see what that looks like. So x over 2 plus 1 is looking something like this. Actually, here. That's the graph of x of y equals x over 2 plus 1. And we're saying that the function value looks like this line when x is really large. So on the far right-hand side of the graph, we expect the graph to look more and more like a green line. This green line is called the slant asymptote, which describes the behavior when, let's say, as x runs to plus or minus infinity. Okay? If you do the calculations, as a matter of fact, if I change this x going to infinity to plus or minus infinity, this argument still holds. This number is still really small, and f of x behaves like x over 2 plus 1. Okay? So on the far left side, the function is going to look like, it's going to get closer and closer to this line. Alright? Although we don't know what the graph of f of x looks like, at least writing it this way gives us some idea of what the function looks like on the far right and on the far left. Okay? So the slant asymptote describes the behavior as x goes to plus or minus infinity. It shows what the graph looks like at those locations. Okay? Especially useful for rational functions. Another word for slant asymptote is oblique asymptote, and your author uses both. Okay, so like I said in the beginning when I started this class, that we're going to look at two parts. This first part was limits at infinity. This second part is infinite limits. Okay. We'll start with a picture. So, according to this diagram, if I pick values of x that are getting close to 0, then consider the corresponding y values. So as we run close to 0, y values get larger. And the closer to 0 that I go, the larger the y values can be. And you can make y as large as you want. That statement is the key to infinite limits. That to say the limit as x approaches 0 from the right, which is what this picture shows, of f of x equals infinity, I'll repeat what I said earlier, means that f of x can be made as large as we want by making x close enough to 0. Okay? And that's how we write it. When your limit as x approaches a number is infinite, that's described as an infinite limit. Something similar happens on the left-hand side. So if we pick a value of x and take the corresponding value on y, as x gets close to 0 from the left-hand side, the values of y fall as far down as we want. Which means the y values can get as large as you want in the negative direction. Okay? As large as you want in the negative direction. Symbolically, that means the limit of f of x when x goes to 0 from the left is as large as you want in the negative direction, the negative infinity. Okay? And in words we can say f of x can be made less than any number by making x close enough to 0. Let's make a distinction between the two. Okay? Here x close enough to 0 but more than 0. Here x close enough to 0 but less than 0. Okay? Infinite limits define, or infinite limits have a very close relationship with the graph, and we can define something called a vertical asymptote and relate infinite limits to those. So here's the definition for a vertical asymptote. A line x equals a is a vertical asymptote of the graph of this function f of x if either the limit from the right hand side to a is infinite, doesn't matter if it's plus or minus infinity, or the limit to the left hand side of a is plus or minus infinity. And that confirms the existence of vertical asymptotes. The graph I drew over there was the graph of 1 over x. So let me let me write these theorems or these limits as results. There actually is a formal definition with epsilons and deltas for infinite limits, but I won't talk about it. But we can argue this by waving hands. We just say, okay, when x gets really small but positive, 1 over x gets really large, right? And and actually I can make 1 over x as large as I want. And all I have to do is make x really, really small. But positive. So if I want, I could make 1 over x less than anything I want. If I make x close enough to 0 but less than 0. Okay, now these two limits together tell us that we have a vertical asymptote at x equals a. Well, a being 0, so at x equals 0. Okay? So as a rule of thumb, you may be tempted to say, okay, whenever you have a value of x that makes the denominator 0, you have a vertical asymptote. Does that make sense? Okay. Well, that's actually not quite true. Let's see why. Here are some examples. Limit as x approaches to 2 of x minus 2 squared over x squared minus 4. Now what value of x makes the denominator 0? 2 and negative 2, right? And we're running to 2. So will this limit be infinite? Okay, well let's see. We can write x is not equal to 2, right? So if I rewrite this expression as that, right? Then since x is not 2, I can simplify. What is this limit equal to? 0 over 4. Right? So the limit is 0. So do we have a vertical asymptote at x equals to 2? No. Right? Okay. Well, let's take another one. The limit as x approaches to 2 of x minus 2 over x squared minus 4. Again, 2 would make the denominator 0, but we have to still compute this limit. If this limit is infinite, then we have a vertical asymptote. Okay, we're going to do something similar here. And these cancel. What is this limit? 4. Okay. So x equals 2 is not a vertical asymptote either here. Let's take one more. Let's go to 2 from the right-hand side and compute this limit. Notice all three have the same denominators, right? So when x is near 2, x minus 3 is near what? Negative 1. When x is near 2, x minus 2 is near 0. Okay, when x is near 2, but x is more than 2, x minus 2 is close to 0, but positive, right? That's right, 0 plus 2. It's a positive small number. And when x is close to 2, x plus 2 is close to 4. Okay. So this quantity is positive or negative? Negative. And the denominator is really, really small, right? So this expression is really large in the negative direction. Okay. Technically, we shouldn't write this, but it's a good demonstration of why the limit is negative infinity. Okay? There we go. All right. So therefore, x equals to 2 is a vertical asymptote for that function x minus 3 over x squared minus 4. I want to make a comment about infinite limits. Because we said a limit exists if function values approach a number. Here, the function values don't approach a number, they are infinite. Okay? So technically, this limit doesn't exist. But when I write down the limit equals negative infinity, okay, I'm saying the limit doesn't exist, but I'm also saying it doesn't exist because it's infinite. Right? So it's giving us a reason. In other words, the function has an infinite discontinuity at that point. Okay? So let's look at this one. Limit as x goes to 2 from the left, x minus 3, x squared minus 4. Okay? So x minus 3 over x minus 2, x plus 2. And let's do a similar type of argument here. When x is near 2, x minus 3 is near negative 1. When x is near 2 but less than 2, this is close to 0 but a negative number. And when x is near 2, x plus 2 is near 4. So we have a negative number over a negative number. So our limit is approaching something positive. The denominator is really small. The numerator is fixed. So this is plus infinity. Okay? Therefore, x equals to 2 is a vertical asymptote. All right, but we had that conclusion there. Why does this tell us more about the function? Okay, so let's take a picture here. X, y, and we have a vertical asymptote 2. That limit statement is telling us that if we're near 2 from the right side, the function values are near negative infinity, which means they are far down here. So to the right of this, okay, to the right of 2, the function values are near negative infinity. So that's what the graph looks like. This limit tells us that when x is near 2 from the left-hand side, which is the left of the vertical asymptote, our function values are large but positive. So our graph is up here. Okay? Does that make sense? Okay. So to say that you have, just like for horizontal asymptote, to say that you have a vertical asymptote by itself is not enough. You want to study which infinities are on which sides. Yes?
You have to do it for both sides.
Yes?
Why don't we also have an asymptote at negative 2?
Yeah. Yeah. So, yeah, I'll draw it. But so we will have an asymptote at -2, and I think it'll look like this and like this. Okay? If you do your calculations. From the left it'll be negative, from the right it'll be positive. I think. Okay? Alright. Now let's take the limit as x approaches 2 without specifying a direction of this function. Same function, without specifying a direction. What can we conclude here? Well, we know the limit is infinite, but from the left-hand side and the right-hand side, it's not the same infinity. So all we can actually say here is that the limit doesn't exist. Okay? Because from the left-hand side and from the right-hand side, we have different infinities of this same function. Okay. Let me go back and let's complete our study of that rational function. Let's go back to this one. F of x equals x squared minus 3 over 2x minus 4. And after long division, we decided to write this as x over 2 plus 1 plus 1 over 2x minus 4. Okay? Does that make sense? Yeah. Okay. We're interested in studying 2x minus 4 being 0. So this probably has a vertical asymptote at x equals to 2, right? We can't just say that. We have to compute this limit. So okay. So as x approaches to 2 from the left, this quantity is 2, right? 2 over 2 plus 1, that's 2. 2 from the left, so close to 2 but less than 2. 2 times a number that's close to 2 but less than 2 is close to 4 but less than 4. Does that make sense? Okay, so less than 4 minus 4 is close to 0 but negative. So you get 1 over 0 negative, something like that, a small number. So you get 2 plus negative infinity, which is, okay, so the 2 is negligible, it doesn't really matter. 2 and negative infinity, okay? That already confirms that you have x equal to 2 is a vertical asymptote, okay? We had already established the left limit, but like I said earlier, establishing the vertical asymptote is not enough. Let's see how the function behaves to the right of that asymptote. Okay, a similar argument will show